Hi there and welcome to video 13, which is a tutorial on circle theorems. Remember, these videos are mainly for higher AQA Unit 3, and they're for students who previously sat the foundation who are now trying the higher, so they're an introduction to the topics that I'd like you to get right in the exam that would be easy for you to get right. Now, in this video, I'm going to introduce you to the seven circle theorems, make a card or make several revision cards so you've got one on each one that you can revise from, and then move straight on to video 14, which will be all the past exam questions on circle theorems using the knowledge we have just gone through in this video. So let's start straight away. Before we launch into the circle theorems, let's just talk about the parts of a circle. So, I'm going to start and draw ourselves out a circle here. Now, a key part of the circle is the center. So you should know that there is a center of a circle. A line from the center to what's the circumference of a circle, I'll deal with that in a second, is called a radius. Okay, this is called a radius. And you can think of it like sun rays, okay, coming out from the center of the sun. So a radius. Now, a line that goes through the center from one edge of the circle to the other, but it must go through the center, is called a diameter. So this one here is called a diameter. Okay, and you should see from that the diameter is obviously 2 lots of the radius, so it's 2 times the radius. Because the radius just goes from the outside to the center, the diameter goes from the outside to the center and back to the outside. So they're 3 important things of a circle. The distance around a circle, well, the distance around any shape is usually the perimeter, but a circle's got its special name for its perimeter, and it's called the circumference. Okay, the circumference. So that's the whole distance around the outside of a circle. Then we need to know a couple of new definitions. Okay, so I'm going to try and use a different coloured line for these ones. We probably know this from my circles video. Now, a part of, let's say, a line that cuts a circle like that, but does not go through the centre. So the key thing here is it does not go through the centre. I'm going to label that blue. Is what we call a chord. This is called a chord. Okay. Now, the piece of the circle it leaves here, like this whole piece here, is then called a segment. It's a segment of the circle. There's a small segment. This whole bit left over here is a big segment or a major segment. Okay, so there's one thing we need to know. That's a chord. The other thing we need to know is if we take a slice of the circle, like we had a slice of cake, let's say, so we cut a circle with 2 radii to the center, then that part of a circle would be called a sector. Okay, so a sector is like a piece of cake, and a segment is when you cut the cake in sort of an unusual direction, but you don't go through the center. Okay, and 2 last things we should say. Say I take any point in space outside the circle, like here. This is just a point, and I draw a line from that point to the circle so that it only touches the circle. It doesn't cut through the circle. And I'll always be able to find 2 of those points, like one there and one there. These lines here are called tangents. T for touch. They touch the circle. Okay, so any other line would cut through a circle at 2 places, but here it just touches here and touches here. They are called tangents. Okay, so they're all the parts of the circle that I may refer to when I'm going through the following circle theorems. You should be aware of all of these different pieces of terminology. Okay, let's get straight on with some circle theorems. Here's rule 1. Here's a picture that describes rule 1, and rule 1 says that the angle at the center of a circle is twice that of the circumference. That is, again, if they're coming from the same arc. Okay, so the angle coming from an arc at the center is twice the angle coming from the same arc at the circumference. Okay, so so in this case here, B is 2 lots of A. if you struggling remembering that, I sometimes think the population at the centre of a city is bigger than the outskirts of a city. So there's one way of remembering it. Let's just do a quick example here. Here's a typical question for us. It tells us that AOC, the angle at O here, is 96 degrees. It asks us ABC, A to B to C, that one. Well, we know angle at centre is twice the angle at the edge. So if this is 96, this must be 48. Okay? And let's just have another look at this rule. Here's the rule again. Remember, angle at centre twice angle at circumference. If they told us that ABC was 44, A to B to C, this one was 44, what would AOC, what would that one be? Well, it's doubled that one there, so it'd be 88 degrees. Okay, and that's rule 1 covered. Nice, easy rule. Okay, let's move on to rule 2. Here's a picture for rule 2. What rule 2 says is it says that angles in a triangle that's in a semicircle inside the circle must have a 90 degree at the circumference. So a way to write it in the exam, angles in a semicircle contain a 90 degree. Now, this actually is just rule 1 again, because look, remember we said in rule 1, if you take an arc and you look at the angle at the centre, the angle at the centre here, it's a straight line, so it's 180 degrees. Angle at centre, double angle at edge, therefore this angle here must be 90, which is half of that. So really this is just a special case of rule 1, but it's one you've got to quote in the exam. Easy way of writing it, angles in the semicircle contain a 90 degree at the circumference. So in this example, find angle ABC, A to B to C, assuming this is the centre and this is therefore the diameter, AC is the diameter. This is a case of angles in a semicircle contain a 90 degree, so this angle must be 90. Okay, let's take a look at one more example here. Again, here's the rule. Angles in a semicircle contain a 90. It says if CAB is 44, C to A to B is 44 degrees, find BCA, find B to C to A, find this one. Okay, well, if this is a diameter, this is a triangle in a semicircle, this angle here must be 90. So to get this one, you add 44, add 90, you get 134 degrees. And then you take that away from 180, so you do 180, subtract 134, and you get 46 degrees. So BCA is 46 degrees. Okay, let's move on with a new rule, rule 3 here. Here's a picture for rule 3, and what rule 3 says is that if you have an arc like this, then any angle you draw coming out of that arc at the circumference will be the same. So these two red ones are the same. And the way we phrase it, angles from the same arc at circumference are equal. Now it's not just two angles. I could, as long as I start from that arc and I finish back at that arc, that angle there would also equal the other two red ones. So that would be the same there. And I could do that indefinitely. I could go from here to here, and that would be the same. So angles from the same arc are equal. Now don't confuse this with rule 1. All the angles that I'm talking about here are at the circumference. Okay? In rule 1, we said angle at centre, double angle at edge. Here, angle at edges are all the same, as long as they're from the same arc. Okay, quick example. If ABC is 44, A to B to C, this one's 44, they're asking what ADC is. Always label it ADC, call that one X. What's that one? Well, let's define our arc. Our arc could be here or here. Because we've got an A and a C and an A and a C, our arc is AC. So, drawing out lines from here just to show you, that is coming from that arc, and also the 44 is coming from that arc. So X must equal 44. So the angle we're trying to find must also equal 44 because angles from the same arc at the circumference are equal. Okay, another example. This one's just getting everything together so we can see all the different cases. if DAB is 44, D to A to B is 44, okay, and A to B to C is 60. Sorry, let's just do that again. D to A to B is 44, and A to B to C is 60. It asks us to find DCB, that one, and it asks us to find ADC, that one. Okay, so we've got to find these. Now, obviously, X and Y are either 44 and 60. It's about getting it right. Define your arcs. Let's just define our arc and get this one sorted first. DB, there's our arc, okay? And the angle coming out from this is 44, and it must be the same as the X. So X must be 44, and X was DCB, so this is 44 degrees. Okay, take those away for now. That was 44. And then to find the other arc here, AC, what angles are coming out of this? Well, the 60 is coming out of it there, and also the Y is coming out of there. So angle ADC must be equal to 60. So this one is 60 here. Okay, let's move on to rule 4. Rule 4, there's a picture for rule 4. And what rule 4 says is opposite angles in a cyclic quadrilateral add to 180. So opposite angles, the A and the C, add to 180, and the D and the B add to 180. And that's written there. Now, what does a cyclic quadrilateral mean? A quadrilateral has 4 sides, and a cyclic quadrilateral is one whose corners are on the circumference of a circle. So whenever you see a 4-sided shape whose edges are on the circumference of a circle, you know that the opposite angles must add to 180. Okay, so let's try and use this example here. It tells us that ABC, A to B to C is 84. And it tells us that B to C to D is 102, B to C to D is 102. And it asks us CDA, CDA, I'm going to call that X, and it asks us DAB, I'm going to call that Y. How would I work those out? Well, we have a quadrilateral whose edges lie on the circumference of a circle. So we know that this rule about opposite angles must add to 180. So Y must be whatever number it takes to get that to 180, so Y must be 78 degrees. And similarly, X must be whatever it takes for these two to add to 180, and it would be 96 degrees. And let's just take a look at another type of question with this rule. Opposite angles in a cyclic quadrilateral add to 180. Here's a question, it shows us a quadrilateral. It asks us, is this a cyclic one? I.e., could I draw a circle around this so that it perfectly each corner was on the edge of a circle? Could I do that? Well, I'm trying to do it here with a circle. I'm not getting much success, but that's not a proof. That doesn't tell us anything. What we do know is if it was a cyclic, the opposite angles had to add to 180. Now that one and that one add up. When you add them up, they add to 179 degrees. They don't add to 180, so they can't be cyclic. So the answer to this is no. Okay, right, we've got 3 more rules to go. Let's just get through these as quick as we can. Here's rule 5. It's called the alternate segment theorem. It's a fairly complicated rule to remember, but if you just try and visualize this picture, it says whenever you have a tangent, remember a tangent is a line that touches a circle at one place here. When a tangent meets a chord, and this is a chord, remember a chord is a line that cuts a circle not going through the center, then the angle the tangent makes with the chord is equal to the opposite angle in the resulting shape, is equal to this angle here. And similarly, it works from the other side of it. The tangents meeting the chord this side, so this angle must equal the opposite angle in the resulting shape over there. And mathematically, the way we say it is the angle between a chord and a tangent is equal to the angle in the alternate segment. This one is equal to this angle in the alternate segment. This one is equal to this angle in the alternate segment. In the exam, you can just quote alternate segment theorem. So here's an example. If BAD is 19, B to A to D is 19, they want to know what ACB is, A to C to B, this one here. Well, we've got a tangent meeting a chord, and they meet at 90 degrees. Therefore, the angle in the alternate segment, that one, must also be 19 degrees. And it's as simple as that. Now, they didn't tell us this, but imagine they told us that one there was 104 degrees. This is a tangent meeting a chord at 104, so the angle in the alternate segment opposite here must also be 104. Okay, and that's rule 5. Finally, we've got rule 6 and 7. I'm going to do this all in one and do a couple of examples, and then we're finished with these circle theorems. So here's a picture for each of the rules, and rule 6 tells us that when a tangent, a line that just touches a circle, meets a radius, they always meet at 90 degrees. Always make a 90-degree angle. Okay? So, a tangent and a radius meeting at a 90 degree. Here's last rule, rule 7. It tells us that two tangents to a circle from the same point in space. So here's a point in space. I've drawn a tangent to that circle. Okay, so it's touching here. It would keep going on. It wouldn't cross the circle, and touching here. They are the same length. They will always be the same length. Okay, these rules tend to come up in sort of mixed questions. So let's just have a go at a couple of questions and finish there. These are our last two rules. Let's take a look here. PT is a tangent to a circle centre O. TU is a chord. There's our chord. And angle PTU, P to T to U is 54. Find the size of angle TOU, so this angle here. Now, TO is obviously a radius, because it's a line from the centre O, it tells us the centre is O, to the edge of the circle. When a tangent meets a radius, the whole angle is 90 degrees. Okay, now if that whole angle is 90 and just this part of it is 54, this must mean that this angle here is equal to 26 degrees. Okay, now this is a triangle made of two radiuses, so it's an isosceles triangle, so this one also must be 26 degrees. And then to get the angle at O, you do 180 minus 26 minus 26. And you get 128 degrees. So this one here is 128 degrees. The reasons, I would say, tangent meeting a radius meet at 90, therefore angle UTO is 26, but this triangle here is isosceles, so the angle at U is 26, therefore the angle O is 180 minus 26 minus 26. And last question, PA and PB are tangents to a circle. We know that two tangents coming from the same point, when they meet a circle, they must be the same length. So that length is equal to that length. So we've got an isosceles triangle. It tells us this angle is 68. Work out PAB. P to A to B. Work out that angle. Well, you know that if this and this are the same length, then this angle and this angle are the same. So this must be X. This must be X. We're trying to find out that. So we know that 2x plus 68 must equal 180. And solving that, 2x must be 180 minus 68, which is 112. And so we know that x must be half that, which is equal to 56 degrees. And the angle PAB is therefore 56 degrees. Okay, so those are all the 7 circle theorems that you need to learn. Have a revision card or a couple, try and get 2 circle theorems on each revision card and learn all those. Move straight on to the next video now, which is going to be all the past paper questions on circle theorems, and you should be able to answer them all using the knowledge you've learned in this video. Thank you for watching and good luck in your revision.